Okay, let's begin.
Okay, someone tell me how to do the first one. Let's get through these quickly. Yeah?
You can just plug in one.
Just plug in one, right? It's the easiest one there is. First thing you do is check if you can plug in. Here the denominator is x squared plus 1. That happens to never be 0, so pretty much any number I put here is going to be fine. We get 0 over 2, so 0 is the answer here. B. Yeah?
You can take -1 as a factor from the top and then factor the bottom.
Okay, so first thing you would think is try to plug in. Clearly the denominator is 0. So you want to try step 2 and simplify. And you factor out a -1 from the bottom, and the bottom factors into what?
1 minus x is
Right, that's the difference of squares. That cancels that. And so, yeah, now you can plug in. Here's a half, minus half. C. Plus 1 thirds. How do you do that one? Yeah?
You can try to factor it because the bonus difference of squares.
Right. So again, you can't plug it in. Bottom factors into x minus 1, x plus 1. So that cancels that. Now what?
You can try to plug them all, but it's still 0, so it doesn't exist.
Not so fast. No. Yeah.
You can try look at where the if you plug in like the values close to either side, so you could plug in like 1.5 and 0.5, you can see that's
1.5 way too big. You'd want to think like 1.001
yeah, but
and like minus 0.99999. The numbers like you want super close. 1.5 is way too far. But yeah, you thought of it in terms of tables of values. I'd probably think of it in terms of the graph. That's just a 1 over x graph shifted to the right by remembering the transformation of functions. And you'll notice that as you approach one from the right, it's going to positive infinity, approach one from the left, it's going to negative infinity, so this happens to not exist. So it does not exist is the right answer, but you have to be careful because possibly the graph did something else. So just because you couldn't plug in doesn't mean you jumped, it does not exist. If both sides go, if I had done this, now that's infinity is the answer. Right? So be careful. Okay, verse 3. Now things start to get interesting. A little. Still taking our. We don't know much about limits yet, so still taking our time here. Okay, what about this one? How do you approach this? Did you have your hand up? Oh, okay. What did you try?
Well, so I was plugged in, doesn't work because you divide by 0 and can't do that. You can't factor anything. And then I looked at the graph. The graph is after the y-axis, it's just y equals 1, and before the y-axis, it's y equals -1, and is.
Okay. So you can think of the graph here. It's like that. And this is at 1 and minus 1. Okay.
And there's no the two side limits aren't equal to each other, so there's no.
Right. So from the right you get 1, from the left you get -1. By the way, knowing that that's the graph, how do we know that? You have to recall the fact that the absolute value of x function is a piecewise function. Its x if x is positive, or non-negative, minus x if x is negative. And so that's something you should have in mind. So you remember the absolute value graph, y equals absolute value of x looks like a V. Notice on the right side, this is the graph y equals x. On the left side, this is the graph y equals minus x. So you can figure that out from the graph because when you're looking at absolute value and 0 is an issue, you have to worry about what if I'm on the left or right side of 0 because things can change that way. So here, you realize that you have one or two options here. If you're coming from the right side of 0, your absolute value just returns x. And if you're coming from the left side of 0, your absolute value will return minus x. So you end up with 1 or minus 1 as the answer by simplifying. I mean, it can't be 0 here, but technically, because x in the denominator. You end up with that. So your 1 coming from the right side, your negative 1 coming from the left side. So we can say it does not exist. So have to remember how absolute value behaves. Questions on that one? Okay, what about E? What's the answer? You should recall that arctan x is just another way to say tan inverse. It's the inverse tangent function. Right? Remember, that doesn't mean 1 over tangent, that's cotangent. This means tangent inverse, it's a notation. Some students often think of this as 1 over tangent by mistake, so they came up with a new notation, which is the arctangent. But yeah, how do you figure that one? Yeah.
Start by graphing it.
Right.
So it's just tangent reflected over y equals x.
So do you remember how, right, you reflect one branch of the tangent about y equals x, that's the middle one. You remember what the asymptotes were here?
They pi or negative
No. Remember, tangent is sine over cosine, so it's undefined where cosine is 0 when it's cosine is 0. Pi over 2 and minus pi over 2, you reflect that in y equals x. So you have an upper bound of pi over 2, and you have a lower bound of minus pi over 2. And the arctangent graph looks like this. It should pass through 0. So we know the graph of the arctangent, probably the best way to deal with this problem. We don't really have a computational way per se at this point to look at the tangent, and even if when you do learn that in like Calc 2, it's still nicer here to use the graph. I'd still use the graph. Probably the best way to look at the arctangent function as a limit here. So what's the answer? Right, so a little bit of pre-calc coming back there. You have to remember about trig functions and inverse trig functions. Where are we? How do we do with that one? Yeah?
You can't plug in because you get 0, 0.
Sure, because you plug in x equals 0, you get radical of 1 minus 1, which is 0.
So you have to rationalize the expression.
Rationalize. So we want to simplify that. Factoring, you might see, is very difficult, but you should remember you can rationalize things with 2 terms, especially if you want to get a square in there. Avoid temptation. See students do this all the time. They don't like that radical, they just randomly square everything. Totally the wrong thing to do. You can And that actually falls under a blasphemy. That technically is distributing powers across sums, and then randomly squaring is just too crazy. I didn't even put it in the syllabus. But rationalizing was, what do we multiply by?
Plus 1.
Plus 1. So you have to remember to change the sign. This is called rationalizing. This is called a conjugate. Of the expression over here. And we like doing conjugates because now you'll notice in the denominator, this kind of looks like a minus b times a plus b, which we know becomes a squared minus b squared when we multiply that out. So it allows us to square the first term without doing anything illegal. So in the denominator, I know we should have a squared minus b squared. So that's just the first thing squared, which gets rid of the radical, minus the second thing squared, which is the 1. 1 squared is 1. And in the top, we just multiply out. Just multiply. So that simplifies into that. Now you notice that the plus and minus 1 guy x's would cancel. So we're over here. So the radical of 1 plus 3x plus 1 over 3. So what's the answer here? Right now we can plug in 1. Right? Or 0. 0. Now we can plug in 0. 2/3 is the answer. So that function approaches 2/3 as x approaches 0. And that function behaves like this function close to 0. Questions on that? So things like rationalizing, what trig functions look like, what inverse trig functions look like, these are all things I expect you guys to know prior to this class. Can I erase this? I need space. By the way, how I'm writing things out is kind of how I'd expect you to write them out on a test. So you'll notice that I keep writing the limit sign until I can actually plug in the number, things like that. I expect you to follow these norms. G. Okay, what's the answer? Yeah?
0.
0.
Oh wait, no. Yeah.
Why?
It's because there's bigger powers in the bottom than on the top, so the bottom's gonna go faster.
Exactly. It is 0. And it's bottom heavy. Right? Recall last class, I told you about a bunch of relationships. Among those relationships was the fact that x to the a is much smaller than x to the b as x goes to infinity, and b is greater than a. So pretty much when it comes to polynomials and x is going to infinity, the biggest guys have the say. So you pretty much identify the guys with the largest powers, right? Now for the numerator, the x cubed is going to control everything. These guys essentially don't matter as you're going off to infinity. They might as well be 0. They might as well not have shown up, right? Similarly, these guys don't matter if as x is going off to infinity. So really this function is going to behave like minus x cubed divided by 2x to the fifth. And since the x to the fifth is going to greatly overwhelm the x cubed, the denominator is overwhelming the numerator. You get a fraction where the numerator is very small and the denominator is very large, and that gives you 0. There's a computational way to think about this, which I don't care. For me, this is fine. You can write this and that's showing your work. But some people might be upset if I don't at least mention this, so I'll mention it just one time. Computational way to look at this. Well, pretty much the last 3 GHI, not the insurance company, these problems here. So we have, if we look at, the trick for these is to divide by largest power of x in denominator, always the denominator. Find the biggest guy in the denominator and divide everyone by that power of x. So for g, we would end up with 4 over x to the fifth plus x over x to the fifth minus x cubed over x to the fifth. So it's like you're multiplying and dividing by the same thing. You're not actually changing the values of anything. 2x to the fifth over x to the fifth minus 3x squared over x to the fifth plus pi x over x to the fifth plus radical 2 over x to the fifth. Simplifying, we would get 4 over x to the fifth plus 1 over x to the fourth minus 1 over x squared 2 minus 3 over x cubed plus pi over x to the fourth plus radical 2 over x to the fifth. And now the ambiguity should be all gone, because notice that we have a bunch of fractions here where the numerators are constants, not going anywhere, but the denominators are approaching infinity. So each of these here will go to 0. So you see essentially they didn't matter. And so this becomes 0 over 2, which is 0. You can actually use that technique on all of these to come up down to your conclusions. But because of the relationship I gave you, you should pretty much be able to look at these 3 and know the answer within a few seconds. Let's go to H. Okay, someone else take a crack at this one. Anyone? Yeah?
Negative infinity.
Negative infinity, explain.
Well, because the top is much larger than the bottom.
Well, specifically, the power of x in the top is larger than the largest power of x in the bottom. Say it that way, right? So again, identify the biggest guys because they're the ones who control things when you go off to infinity. So this guy is going to behave like minus 6x to the fifth over 2x cubed. You can ignore the 4s and the 7s when you're going to plus or minus infinity, essentially. So now you realize that you have an x to the fifth divided by an x cubed. That's just going to simplify to x squared. X, right. So now you know the answer is infinity because you have the largest power is on the top. It's top heavy. But I believe we did an example last time where this came up as well. You're not sure if it's plus or minus, so how do you determine that it was negative infinity?
Actually, I think it's positive. I didn't see its x towards negative infinity, so
Okay, so if your x is negative infinity, your x to the fifth would be negative, right?
yes. And the whole-
Times a negative 6, so that would be positive. So the top is going to a positive number. In the denominator, x cubed, it's a negative. You're multiplying by a positive 2, so it stays negative. So you have a positive huge number over a negative small number. Negative infinity is the answer. What's this one? Yeah?
Negative infinity again?
Negative infinity?
Yeah.
Did I hear someone else say something? Yeah?
So negative 17 minus.
You're not here. Who do you agree with? Or him? Negative infinity. Why? Explain.
Because it's on the top, it's top heavy, right? And
Well, what's the highest power in the top?
3. Also, it's
So it's this. And what about the bottom?
3.
It's also 3. So the highest one isn't in the top. So what is that?
This is it.
It's negative 17 over 2 is going to be the answer. And this is called the ratio of leading coefficients. Again, if you divided top and bottom by x cubed, these would cancel, leaving you with 17 top and minus 2 in the bottom, while all the others will have an x in the denominator. Some power of x in the denominator, they'll all go off to 0, leaving you with a 17 divided by minus 2. It's minus 17 over 2. So again, identify the largest guys, pretty much ignore everyone else because they're not going to matter when you're going off to infinity. So this guy behaves like 17x cubed divided by minus 2x cubed. The x cubes cancel each other, and you're left with that. So that one actually went to a number, a finite number. Now GH and I dealt with a special class of limits, so I think I actually want to just summarize those. Have a special technique. So remember in step 2, in the steps to do limits, I think step 3 is where I said, oh, a special technique would apply here. This is one of them. So GHI shows a special technique. And this is the case limits at infinity of rational functions. It turns out for these guys, you don't have to think very hard. There are only 3 cases and they're pretty easy to identify. So it's nice to just know that as a class of limits that you can deal with easily. So P of x, Q of x are polynomials. Of course, assume that Q of x is not 0 here. Then if you're looking at the limit as x goes to plus or minus infinity of P of x divided by Q of x, it turns out there are only 3 possibilities, and we just went through all of them. One possibility is you'll get the answer 0, and that's if the degree of Q is larger than the degree of p. Besides, this, for example, means degree of q. It means the largest power of x in q. So talk about the biggest power in q when that is larger than the biggest power in p, right? So the power down here is bigger than the power up there. You will get 0 as the limit. You don't even have to think about it, really. Right? The calculations would be what I showed you over here by dividing everyone by the denominator, but that's what it's always going to end up being, and we call these bottom heavy. So that's one possibility. Another possibility is you will get plus or minus infinity. You have to pay attention to the signs and know which sign to pick. This happens if the degree of p is larger than the degree of q. Watch the signs to know if plus infinity or minus infinity. And these are top key. So you'll either get 0, you'll either get positive infinity or negative infinity depending on the signs of the things that are there. Right, so you have to watch the coefficients and watch the sign of the power of x. Once you determine the sign of the overall fraction, you know infinity is what you're going to attach to it. And the last possibility is the leading coefficient of p divided by the leading coefficient of q. This happens when the highest powers are the same. And I might refer to such a scenario as the ratio of leading coefficients, because you literally take a ratio of the leading coefficients. So this is a special technique, right? So when you're looking at limits, oh, I couldn't plug in, oh, I couldn't simplify. One thing you can look for immediately is, does what I'm looking at fall into this category? If it does, it'll be easier, of course, than you trying to graph it, right? You don't want to graph those functions. That'll take you forever. And in general, it's probably going to be complicated to write down in general, but in general, looking at comparing this kind of ratio to the list of functions that I gave you before, the fact that the log is less than the exponential, less than polynomials, is less than the exponential, is less than etc. Again, you can compare weight, right? You'll notice that the guys on the right are heavier than the guys on the left. And so you can determine if something is top heavy or bottom heavy, even in cases where it's not strictly speaking a rational function. Yeah?
So could you do the leading coefficient thing if you had like 2 to the x on top and bottom?
Yeah, so if I had something like limit as x approaches infinity of 3 times 2 to the x minus 2x squared over 4 ln x plus 2 times 2 to the x, for example. So the functions that show up, I have exponentials showing up, I have a polynomial showing up, I have a log showing up. I'm going to infinity, these guys do not matter. The exponentials are going to control because they're the biggest, they're the heaviest. So now I look at it and, oh, it's the same exponential, so it's just going to go to the ratio of the coefficients. That would be 3 over 2. Had this been a 3 to the x, the answer is now 0. Had that been a 3 to the x and this was a 4 to the x, the answer is now infinity. So you can generalize this principle to bigger things if you pay attention to the weight of things here. other important facts that lead to special techniques. Suppose I have three functions f of x, g of x, and h of x. Suppose these limits exist, so they do give us some meaningful answer. Then if you have the case where f of x is always less than or equal to g of x when x is near a, or for all x near a, right, that way, then the limits will share the same relationship. So if you know inequalities, how functions fit into an inequality, the limits will also fit into the same equality, right? Now that you can kind of figure out from the definition of limits. Limits are tracking the y value when your x is approaching something. If the y values over here are always larger than the y values over here, then the y values you get close to will be larger than the y values this get close to. Okay? And the limit is just what the y value is getting close to as x approaches a. Right? So limits will maintain inequalities. That's one important fact. Moreover, there's another important fact, which is another special technique, I would say. Can anyone guess what I'm about to write down? You can probably guess, since I started throwing in inequalities. Well, some of you should know at the moment I start writing it down. Using this, you can prove something called the Squeeze Theorem. AKA, very rarely it's called the sandwich theorem. And that basically says the following. If we know this relationship holds, and moreover, you know that the limit as x approaches a of h is equal to the limit as x approaches a of g. Let's say they're both L. Then, if I take the limit of all these guys, the limit will maintain the inequality. And both ends I see going to L. So limit of f is sandwiched between the two L's, or it's squeezed between the two L's. So you end up in a situation where you see that the limit of f is less than or equal to L, and at the same time is greater than or equal to L. The only way to reconcile that is that the limit of f must be L itself. This idea is called the Squeeze Theorem. If I know what's going on to the endpoints and they're the same number, any one in the middle is forced to also be that number. I will do even better. I will give you guys some examples to try. And on Tuesday, we'll see where you got with them. Which is even better. So with that fact in mind, try to do these. And on Tuesday, we'll go through them together. Turns out the trick with these three is actually the squeeze thing. I have one more set of special techniques to tell you about, and then I'll let you go. Oh, then I'll give you, I have quizzes to get back. Then I'll give you your quizzes back and let you go. The squeeze theorem in some geometry can prove these things that I'm going to dub the special trig limits. You don't need to know the proofs. You can read them in the textbook if you're interested. But the first one is the fact that the limit as x approaches 0 of sine x over x is what? Who knows? Yeah? It is 1. By the way, this implies the second one right away. Limit as x approaches 0 of tan x over x is also 1. Because that's just like this thing divided by cosine of x. Cosine of 0 is 1, so it doesn't actually change the value. I want you to note here, the reciprocals work because it's 1. So you can think about something like the x divided by the sine. It'll still make sense, it'll still be 1. Just that whenever these two functions appear together, they grow very similarly when they're near 0. They give you very similar values. One and some algebra can prove the last special trig limit, equation 3. That guy equals 0. Examples for next time. There. So try those 6 examples on your own. We'll start last one next time. I'll see you guys on Tuesday.